Hello, everyone. Welcome to this short session on dust and nebulae. When I watched a recent video by Queeve the Lazy Geek regarding city versus country astrophotography contest with Nico Carver, they were actually taking a picture of the Pleiades nebulae from the city and from the dark skies and comparing their results. What could they get? But during the course of their discussions, it also ventured on talking about the reflection nebulae because there's a lot of dust in the Pleiades region, and that dust looks well. It's the interstellar dust, and it has a tint of blue in it. So then it's also called the reflection nebulae. Now they spoke a little bit about what are like the reflection nebulae, and then there are dust which looks dark and it's not really reflecting anything. So I just wanted to shed a little bit of light on what is the dust and interstellar dust, and how it can either reflect light or it can look a little bit red or dark. So here I have two examples, rather four of them, but they're classified in two. So I have the top row. You can actually see in the top row. On the left, I have the Horsehead Nebula in Orion, and a zoomed in version of it is over here. And then I have the Elephant Trunk Nebula, and over on the in the right. And then in the bottom left, I have objects which are completely in contrast with the top row. I have the blue open cluster of Pleiades, and there's a lot of gas here which is looking blue. And then I have the Witch Head Nebula, again another nebula in Orion, which is very near the bright star Rigel. So what is the difference between these two systems, and what is the physics behind it? So let's try to look at it in slight detail. Well, this is what we call as the interstellar dust. It's the dust that fills between the stars. In it's all these objects, all four of them, are part of our own galaxy, the Milky Way, and the dust, therefore, basically they are the molecular clouds. They could be metals, the carbon monoxide, ammonia, silicates, and other molecules made up of carbon, hydrogen, oxygen, and nitrogen. And there's also water and ice. These dust grains are basically a result of stellar outflows. So whenever you have new stars which are forming, the solar systems will be formed, and there would be dust which would be left out, and that would actually go out into the further reaches of our galaxy. Or even when stars are dying, they go into what we call as the red giant phase, and then they eject the exterior atmosphere. And that exterior atmosphere, is a lot of that is actually made up of these molecules because they're a result of the end of the fusion cycle, nuclear fusion. So they go out into the galaxy, then form what we call as the interstellar dust, and it fills the spaces between the stars. The size of these dust grains is actually around micrometers. That is again, which we really understand from physics. The light of similar wavelength will interact with objects of the similar dimensions. The dimensions of the objects with which light interacts, there's almost the same dimensions scale as the wavelength of light itself. And the dust is interacting with the light from infrared to UV with visible in between wavelengths. So, and the size, the wavelengths are around micrometers, and that's what the size of the dust grains here is as well, micrometers. Now, what really happens when light from bright nearby stars here, for instance, here you see lots of the blue stars in the Pleiades. They're hot stars, and then there's Rigel in Orion over here. So, what really happens when light goes through these dust grains? Well, it can go into the vibrational degrees of freedom. That is, these molecules can vibrate. Imagine that they're attached by a spring. So the carbon and oxygen, for instance, here, they can vibrate, and also they can rotate. So there can be an axis, and they can rotate around. So the light will basically go into this vibration and rotational degrees of freedom. Now there could be lots of resonant levels there. We will not go into the microscopic details as to what all interactions happen, but an overall picture is that it leads to absorption and scattering. So light scatters off from these dust grains, and it can also lead to what we call extinction. That is, the what if you started off with original intensity, and the intensity which you get when light has actually passed through the dust grains is slightly lower. So what really happens is you have light of various wavelengths, from longer to shorter wavelengths, which is impingent upon the interstellar dust. What really happens is the red wavelengths, which are the longer wavelengths, are able to transmit through the dust, whereas the bluer wavelengths get reflected. They undergo a reflection due to higher scattering. Scattering is dependent upon wavelength, and the shorter wavelengths get reflected. So depending upon where you are when you are viewing these objects, if you are at position A, it will lead to dark reddish brown nebulae with low intensity. That is what is happening here. For instance, in Orion, you see a lot of dust here. This dust is actually in the foreground of this red emission structure. So therefore you see that the intensity is diminished, and also the dust looks uh, dark reddish brown. And the same case here in also in the Elephant Trunk Nebula, where you have all these dusty patches. They're all in the foreground, and they look dark reddish brown. Whereas in the lower half, on all these objects, we are actually sitting at position B. So since we are sitting at position B, we are actually observing what is blue light. So in position A, the original light gets de-blued, and that is what we call interstellar reddening. And in position B, we are basically seeing that blue light which was de-blued in that A case. So that is why we see the reflection nebulae look seem bluer rather than dark reddish brown. Incidentally, the same thing is also happening in our own atmosphere. When we look at the sky, the atmosphere is also it does the same thing. The light gets scattered in our atmosphere, and therefore if you look at the sky during daytime, well, the visible wavelengths, they're coming from the sun. Now during daytime, the sun is overhead, it's high up in the sky, so therefore the blue light which gets scattered gets to you immediately, and then you see the sky is indeed blue. Whereas when the sun is near the horizon, when during sunrise or when sun is setting near the horizon, light has to go through a much longer path through our atmosphere, and only the red wavelengths get transmitted through that longer path. And that is why you see during sunrise and sunset, the sky appears red. That is the atmospheric effect of the reddening of the sky, which is similar to the interstellar reddening which we see over here. So that's the physics of interstellar dust, and when we see the dark brown nebulae, and when we see the blue reflection nebulae. I hope you you found this information useful and understand how things are really working on, and how universal the phenomena is, whether we are watching things here on Earth regarding our own sky, or whether we are dealing with the interstellar dust.